So alternatively, we could use recursion as long as we're fairly confident with it. The recursive approach is more elegant, but is considered inferior to the iterative version in some programming language like Python. This is because the space we used in the runtime stack is variable between different programming languages. And on the plus side, we can use a simple scene set and just pass one parameter, which is parent. So this will make our code look like much bigger, simpler. There are three edge cases. The first is if we have unknowns, but after we finish the algorithm, we have been only seen 3 nodes, which is less than 4. So this case means we didn't reach all the entire of the graph, so it is not a valid tree. Another edge case is if when we check the neighbor, we find the neighbor is already in scene before. In that case, we should return false because it will form a cycle, and a cycle is not a valid tree. Another situation is if we start from the node and we check the neighbor and we find the neighbor is equal to parent. In that case, that means the neighbor is the parent. It forms a bicondition node. So we use continue to skip this trivial cycle, and it will trace back to the node and check if the node is in the scene, return. So first, let's create a scene set, which is empty set that will record the nodes we have already been seen. And then we create depth first search function. It have 2 arguments. The first one is the node, and the other is parent, which is the node's parent. So we input 0 to node, and we let the negative one become 0's parent, because 0 is the root node. So first let's check 0. 0 is unseen before, so we record it into the scene set. And now we check the adjacency list at node 0, which have 3 elements 1, 2, 3. And first we start from the neighbor is 1. When neighbor is 1, 1 is unseen before, so we record 1 into the scene set. And we check the adjacency list at node 1. It have 2 neighbors, which is 0 and 4. So first we check the neighbor 0, which is equal to 1's parent. So we use continue to skip this trivial cycle. And then we check 4. The neighbor 4 is unseen before, so we write them into the scene set. And we check 4's neighbor, which is 1, which is equal to 4's parent. So we use continue to skip the trivial cycle. So we have to trace back to the node 4, which have already been seen before, so we have to finish this depth first search, which will report true, and we trace back to the node 1, which is also seen before, so we have to finish this whole depth first search about node 1, which will report true. And let's keep move on to the next neighbor of the node 0, which is the neighbor 2, which is also unseen before. So we write 2 into the scene set, and then we check 2's neighbor, which is 0, which is equal to 2's parent. So we use continue to skip this trivial cycle, and then we trace back to 2, which is seen before. So we finish this depth first search, which will return true, and then we can move on into the next neighbor, which is 3. But 3 is unseen before, so we record 3 in the scene set, and then we check the neighbor of 3, which is 0, which is equal to 3's parent, and we use continue to skip this trivial cycle, and it will trace back to 3. But 3 is already seen before, so we have to finish this depth first search, which will return true, and then it will trace back to node 0, but 0 is also seen before, so we have to finish the overall depth first search about node 0, which is also equal to true. So the depth first search at node 0 and parent negative 1 will return true. That means there's no cycle in the node 0's graph. And then let's check scene set, which will automatically sort it as 0, 1, 2, 3, 4. And we check the length of the scene is 5, which is equal to a node. So it will also return true. That is mean the entire graph is fully reached. So because the both sides is overlapped is true, and the intersection between them is also true, so it is a valid tree. So first we create a variable scene. It is a set. It will record what we have already seen. And then let's start. First, we define depth first search. It have two arguments. First is node, and other is the parent of the current node. And first, let's consider the edge case. If node is already in scene, in that case, we directly return to involve to avoid the infinite looping. And other case, if node is unseen, then we add them to the scene set, so it will mark already been seen. And after this edge case, we should use the for loop for neighbor in adjacency list at node. So this will check all the neighbor of the current node. And let's start this for loop. First, we should consider the edge case. If the neighbor is equal to parent, that means the neighbor is the parent. If the neighbor is the parent, so it should be the child of the node. But if it also is the parent, that means it is biconditional connection. So both incoming and outgoing in the opposite direction. So in that case, we should use the continue to skip this trivial cycle. And other case is if the neighbor is in scene. That means it already seen before. If it is seen before, it will form a cycle. If it forms cycle, it is definitely not a valid tree. So in that case, we will directly return the false. And after we consider these two edge cases, we execute them and we use the result to hold the Boolean value, which is the depth first search. We recursively run this depth first search. Now we put the two arguments. First is neighbor. The current neighbor become the node, and the current node become the parent. And then we should check if the result is not true. At that time, we return false, because if it is not true, only one reason it is not true. It is must contain cycle. If it contains cycle, it immediately return false. And after it escapes this, we return true, because if it passed the algorithm, it must be continue or return or reach the end. At that time, we just return true. It is not contain cycle. So finally, in the out function valid tree, we should compare return depth first search. We give them two variables. First is 0, which is our starting point, and other is -1, which is our artificial make the parent node of 0. That means the 0 is root node. It didn't have any parent. And we also should make sure the length of the scene is equal to n. That means we already checked the n nodes. So if we already checked the n nodes, that means we reached the entire graph. It's already been seen as n nodes. So if both of these two is true, only that we can return true. That is valid tree.